If you've ever used an AI chatbot to, like, help write an email or maybe summarize a long article for work, you have almost certainly caught it confidently lying to you.
Oh, yeah, absolutely.
Right. It will just invent a fact or cite a source that totally doesn't exist, and it does it with the utmost authority.
Yeah, it's
In
wild.
the tech world, they call it a hallucination. And, it's annoying when you're writing a blog post, but I want you to imagine a totally different scenario. What happens when that exact same underlying AI technology is looking at a patient's chest X-ray?
Well, the stakes go from, you know, slightly embarrassing to potentially life-threatening in a heartbeat.
Exactly.
You simply cannot afford a confident hallucination
Oh,
when someone's health or, like, their specific course of treatment is on the line.
exactly. And that is why we are here. Welcome to today's deep dive. Our mission today is exploring a really cutting-edge research paper titled Visual Alignment of Medical Vision Language Models for Grounded Radiology Report Generation.
It is a fascinating paper.
Right. It really is. We are digging into this massive problem in AI healthcare, which is, these models just making things up, and a brilliant new solution called VALOR. This paper outlines exactly how scientists are forcing this AI to stop hallucinating and, well, actually look at the facts.
And then to really set the scene for you, since we're in audio, I want you to use the theater of the mind here.
Okay, paint a picture.
Picture a modern, softly lit medical bay. Imagine glowing chest x-rays pulled up on massive high-definition monitors. But overlaid on those images are these cascading streams of code.
Oh, wow.
Right. The stakes in this room are incredibly high because automated radiology report generation, or RRG as it's called, could massively reduce doctor burnout.
Because they have to look at so many of these?
Exactly. We have radiologists looking at hundreds of complex images every single day. If an AI could draft a, highly accurate initial report, it would be a total game changer for the medical field.
A huge time saver.
Huge. But that entire future hinges on one word, and that word is trust. We can only deploy this tech if we can completely trust the AI.
And the sheer confidence of these AI bluffers is what terrifies me, honestly. Okay, let's unpack this core problem. We need to look at the baseline model they tested here.
Right.
We are dealing with large medical vision language models, or MED-VLMs, and the researchers in this paper, they look at a baseline model called Elavi Med version 1.5.
Yeah, a very standard model.
And they give this terrifyingly specific example. The AI is looking at a chest X-ray and confidently writes out a diagnosis of consolidation or a pneumothorax, which is a collapsed lung.
Right. It generates this perfectly formatted, highly professional medical report stating that those severe conditions exist.
But neither of them are actually in the image.
Not at all.
The X-ray is totally clear of those specific issues. The AI is just entirely making it up. To me, it's exactly like a brilliant medical student who has memorized every single medical textbook ever written, but they are just too lazy to actually walk over and examine the physical patient.
Yeah, that's a great way to put it.
So they just sort of glance from the doorway and start guessing based on what's statistically probable for a patient complaining of a cough.
What's fascinating here is that your lazy medical student analogy is mathematically accurate.
Really?
Yeah, totally. Because these models are built on massive, text-heavy, pre-training corpora.
Meaning just tons of reading material.
Exactly. That means they have read millions of pages of medical literature, journal articles, textbook definitions. And because of that specific diet, they haven't actually learned genuine cross-modal reasoning.
Okay, meaning they aren't translating between the visual world and the text world.
Right. They aren't truly connecting the visual pixels of the X-ray they are shown to the actual text they are generating. They're heavily relying on learned text patterns.
So it's not looking.
No. If you feed it an image of a chest, it recognizes chest, but then it just triggers a highly sophisticated game of medical predictive text. It's just guessing based on what words usually follow other words in those textbooks it read.
Oh, wow. So it's playing the odds of language, not actually practicing medicine.
Precisely. It knows that the word plural is statistically very often followed by the word effusion. So it just outputs plural effusion without verifying if the visual evidence of fluid around the lungs is actually present on the scan right in front of it.
Okay, but hang on. I have to ask. If the AI isn't looking closely enough at the image, why not just, train it with a massive cheat sheet?
What do you mean?
Like, take 100,000 correct human-written reports, put them next to the X-rays, and use human preference data to tell it, bad AI, this report is wrong, do better. Doesn't that force the lazy student to learn?
You would think so. And To be fair, that is exactly what current state-of-the-art solutions try to do.
Oh, really?
Yeah. But those existing fixes have critical flaws. Let's look at that first approach you just described, which is data reliance.
Hmm.
Specifically, methods like direct preference optimization or MedPO.
Right, where human experts basically sit down and grade the AI's output.
Exactly. The first obvious problem is that it is incredibly time-consuming. And it's prohibitively expensive to get actual highly paid radiologists to sit down and grade thousands upon thousands of AI reports.
Yeah, I guess doctors have better things to do.
They do. But the deeper, more structural flaw is that this optimization happens entirely in what researchers call the textual space.
Okay, stop right there. What does textual space actually mean in this context?
It means the model is evaluated purely on the words it produces.
Just the words.
Just the words. It learns to prefer one sentence structure over another or one medical phrasing over another, but it does this without ever verifying if the winning sentence actually matches the physical X-ray.
Ah, so it's still not looking at the patient.
Nope.
It's just getting really, really good at writing a convincing fake chart.
You hit the nail on the head. It's optimizing for sounding like a doctor, not for diagnosing like one.
That is so wild.
And then there's the second popular fix, which is arguably even riskier.
Riskier than making up fake charts.
Yeah, it's called retrieval-augmented generation, or RAG. The idea here is if the AI is confused about an image, let it search a massive database of past human-written reports that have similar-looking X-rays.
Okay.
And then it just pulls information from those old files to help write the new report.
I mean, I don't know. That sounds useful, though. It's like a doctor asking a colleague for a second opinion based on a similar past case.
It sounds incredibly useful until you realize it introduces a dangerous new kind of hallucination.
How so?
Think about the mechanics.
Mm-hmm.
The AI might retrieve a past patient's file because the overall lung shape is similar to the current patient.
Right.
But then it accidentally copies a specific localized finding, let's say a fractured rib, from that old file into the new patient's report.
Oh, wow.
Yeah.
So now it's diagnosing you with someone else's broken bone just because you have similar-sized lungs?
Yes. Because, again, there is a fundamental semantic gap. The AI is pulling in external text to fill in its blind spots, but it isn't enforcing a direct pixel-by-pixel alignment between the generated words and the actual visual content of the current image.
It's literally just borrowing someone else's diagnosis.
Exactly.
Okay, let's recap where we are because this is a mess. A human grading system is way too expensive and still doesn't force the AI to look at the image, and copying past reports just imports other people's diseases.
Perfectly summarized.
We need a way to force the AI to align its words directly with the actual pixels of the image in front of it. And we needed to do this without relying on expensive human grading or borrowing other patients' files.
Right. And that brings us to the actual solution presented in this paper, which is VALOR.
Yes, that.
It stands for Visual Alignment of Medical Vision Language Models for Grounded Radiology Report Generation.
Which is a mouthful.
It is a massive mouthful, but it tackles this exact problem in two distinct, brilliant stages.
Let's break down stage 1, which the researchers call clinically informed textual reasoning.
Yes. So before we can force the AI to look at the image properly, we have to make sure it actually knows how to speak the highly specific, nuanced language of medicine.
Right, it needs the vocabulary.
Exactly. So in stage 1, VALOR uses verifiable textual rewards to guide the model. It uses standard natural language generation metrics, things like BLU, Rugel, and BERT score.
Okay, let's quickly define those for you listening. BLU and Rugel, those are essentially algorithms that check how closely a machine's text matches a human's text, right?
Exactly. BLU basically checks how much of the AI's vocabulary overlaps with the human ground truth report.
Like checking its spelling and word choice.
Yeah. While Rugel looks at the actual sequence and order of the words to ensure the sentence structure actually makes sense, and BERT score evaluates the underlying meaning, or semantics.
Got it.
So together, they ensure the sentences are grammatically correct and logically complete.
So it's teaching it basic medical fluency.
Yes, but as we know, basic fluency isn't enough in a hospital. You need precision. So they also introduce clinical metric rewards using specialized tools called Chexpert and RadGraph.
Okay, what do those do?
Think of these tools as a strict, unforgiving grading rubric specifically for precise medical terminology. They scan the AI's draft and check if it is capturing the exact clinical entities like opacity, or effusion, and the specific relationships between them found in a real report.
Okay, but reading the paper, there's a really interesting detail they discovered here.
Oh, the ablation study.
Yes.
Yeah.
The researchers did what's called an ablation study, right? Which is essentially taking the AI framework apart piece by piece to see which parts are actually necessary and how they affect the whole.
Right.
And they found out they couldn't just blast the AI with these strict clinical rewards on every single training step.
This is a crucial, fascinating detail. If you give the AI this strict clinical reward on every single step, the training completely destabilizes. In machine learning, we say the policy collapses.
And policy.
Yeah, the policy is basically the AI's internal rule book for making decisions.
Okay, so why does the rule book collapse?
Well, think about the incentives. If the AI realizes it only gets rewarded for using complex disease terminology, it completely stops trying to write coherent, grammatically correct sentences.
Oh.
Yeah, it just starts rapidly outputting a string of medical jargon to maximize its score.
It's just standing in the corner screaming, pneumothorax, edema, fracture, to get a treat.
Exactly. It literally turns into a medical slot machine.
Hmm.
So the researchers found they have to inject these clinical rewards periodically, only every certain number of steps.
I see.
It gently nudges the AI's rulebook toward clinical faithfulness without breaking its fundamental ability to write natural, readable language. It's a very, very delicate balancing act.
Okay, stage one makes sense. You've taught it the right vocabulary, you've balanced the grammar with the hard jargon, but wait, hold on. So what does this all mean? I have to push back here. Stage one still doesn't solve the core problem we started with.
You're absolutely right.
You've just taught our lazy, bluffing medical student how to sound even more professional and convincing. How do we actually force it to look at the physical X-ray?
And that skepticism is exactly why Stage 2 exists.
Oh?
This is the aha moment of the entire paper. Stage 2 is called Self-Supervised Visual Reasoning. This is where VALOR fundamentally changes the game and forces the AI to finally open its eyes.
Walk us through it. And to be honest, I'm a bit skeptical of the self-supervised part. Are you telling me their solution to an AI hallucinating is to have another AI grade its homework?
I know it sounds.
Doesn't that just create an echo chamber where two AIs just agree on a hallucination?
That is the exact trap they had to avoid. To prevent an echo chamber, they introduce a completely independent, frozen, multi-label domain expert model.
Frozen.
Yes, the key word is frozen, meaning its parameters are locked. It cannot learn bad habits from the main AI.
Oh, I see.
Think of this frozen expert as a veteran radiologist who refuses to write reports. They only look at images and identify disease features. Now, during training, the main AI drafts a bunch of candidate reports for a single X-ray.
Okay, so the main AI rates, say, 5 different possible drafts for what it thinks it sees on the scan.
Right. Then that frozen expert steps in. It takes each of those drafted text reports and compares them mathematically against the actual continuous domain features of the X-ray.
Okay, continuous domain features. That is some dense textbook jargon right there.
It is.
What does that actually look like in practice?
Fair enough.
Yeah.
Let's simplify it. It translates both the text draft and the physical pixels of the image into a shared mathematical language.
Okay.
Imagine translating both an image of a lung and the written word lung into a massive grid of numbers. If the text describes a collapsed lung, but the visual pixels of the image don't mathematically map to those same coordinates, the frozen expert flags it.
Wow.
It calculates an exact image-text similarity score for every single one of those 5 drafts.
Oh, that's brilliant. So the independent expert model is literally scoring how well the drafted text matches the visual evidence in the image. It's bridging the gap between text and pixels.
Yes, but this raises an important question. How do you use that raw similarity score to actually train the AI?
Right.
The researchers do something incredibly clever called using rank normalized advantages. Instead of just giving a raw pass or fail score, the system essentially grades the AI's drafts on a curve.
Oh man, I remember grading on a curve from college. It can be brutal if you're at the bottom.
It is for the AI too, but it's totally necessary. If it just gave a pass-fail grade, the AI wouldn't learn any nuance.
Right.
By taking all 5 drafts and ranking them from best to worst based on which one visually aligns best with the X-ray, the AI learns directional improvement.
Oh, so it sees what it did right.
Exactly. It learns exactly which visual cues made draft A better than draft B. It assigns the highest reward to the most image-consistent candidate. This explicitly steers the AI away from generic predictive text and forces it toward visually grounded outputs.
That is so elegant because, crucially, it's completely self-supervised.
Right.
There are no expensive human doctors sitting around grading these drafts. It's a mathematically grounded AI checking another AI's visual homework. It perfectly blends the textual fluency from stage 1 with this strict, unrelenting visual grounding in stage 2.
Exactly. It completely eliminates the need for expensive preference pairs or dangerous retrieval databases. It just relies on the pure mathematical agreement between the generated text and the actual disease-relevant features in the image.
Okay, here's where it gets really interesting because the paper doesn't just claim this works in theory, they prove it visually.
The attention maps.
Yes, they include these attention maps in Figure 5 of the source material.
Right.
For anyone listening, I want you to imagine a standard grayscale chest x-ray. Now, overlaid on top of it are these glowing heat maps, red, yellow, and blue regions, showing exactly where the AI's eyes are focusing when it writes the report.
It's quite literally visualizing the inner workings of the AI's mind.
It really is, and it's wild to look at. First, they show the baseline model, AvaMed. The attention map for LavaMed is just a total mess.
A disaster.
It entirely misses the lung region. The bright red heat spots are lingering on diffuse, totally irrelevant areas near the outer edges of the image.
Right.
And because it's not actually looking at the lungs, it confidently bluffs and concludes no visible abnormalities.
It completely failed to ground its diagnosis in the relevant anatomy.
Right. Then they show VALOR without the stage 2 visual grounding, so just the text training. It gets a bit closer, the heat map moves inward, but it gets entirely distracted by the pelvis and the very base of the X-ray.
So it's looking at the body, which means it knows it's supposed to be scanning anatomy, but it's fundamentally lost anatomically.
Yeah.
How does full VALOR perform?
When you look at the fully trained VALOR with the visual grounding, it is night and day. The heat map precisely zeroes in. I mean, it is a bright red bullseye, directly on the exact right lung base.
That's incredible.
It spots the opacity perfectly, and because it's looking at the exact right pixels, it generates an accurate, clinically sound report diagnosing atelectasis. It's incredible to see the literal shift in focus. It finally opened its eyes.
The visual proof is really compelling, but the hard numbers back it up just as strongly. The researchers evaluated VALOR on two major benchmark data sets that are standard in the industry, IU X-ray and MMNC's CXR.
Okay.
And they compared VALOR to the state-of-the-art preference-tuned model, AMED-PO.
That's the one trained with the super expensive human grader data, right?
Exactly. And VALOR outperformed it massively. VALOR saw about a 20% improvement in overall generation quality, meaning the reports were more fluent, coherent, and useful, and an incredible 25% improvement in strict clinical accuracy.
A 25% jump in clinical accuracy without using a single human grader is massive.
It really is. But the most impressive statistic comes from the zero-shot setting.
Zero shot, meaning they threw this AI into the deep end with brand new, unseen data it had never explicitly been trained on, just to see if it could adapt.
Spot on. This is a real David versus Goliath scenario. VALOR is a relatively specialized lightweight framework, but they tested it against massive proprietary Goliath models in this zero-shot setting.
Who are they up against?
We're talking about the heavyweights, GPT-4o, Gemini 2.5 Pro, and even highly specialized medical models backed by massive funding, like MedFlamingo and Mayor 2.
These are models trained on practically the entire internet. They have billions upon billions of parameters.
Yes, and VALOR beat them all.
Wow.
In generation quality, VALOR surpassed these massive proprietary models by an average margin of 17%.
That is huge.
Because the giant models, for all their unfathomable power and data, are still fundamentally text-heavy predictive engines. They haven't been forced to visually ground their medical reasoning the way VALOR has.
They're still just incredibly smart medical students guessing from the doorway, while VALOR is standing at the bedside actually examining the patient.
If we connect this to the bigger picture, the implications are profound. Healthcare automation is not some distant sci-fi concept. It is happening right now. Hospitals are absolutely desperate to reduce the administrative load on radiologists so they can focus on complex cases.
But they can't deploy it if the AI is hallucinating collapsed lungs and fractured ribs.
Exactly. And what VALOR proves is that we don't need endless, prohibitively expensive human intervention to make AI safer and more accurate.
We don't need the human graders.
Right. We don't need doctors grading million-line spreadsheets of AI output. We just need smarter reward systems. We need architectures that fundamentally force the AI to mathematically ground its assumptions in physical reality before it is allowed to speak.
It is so satisfying to see a framework that actually cures an AI of its worst habit talking confidently without looking at the facts. It brings us right back to where we started with that annoying chatbot. We figured out how to stop the bluffer.
By simply forcing it to look and giving it the mathematical tools to know what it's looking at.
Which leaves you with a final thought to mull over. If we can train an AI to self-correct its visual focus in a high-stakes life or death environment like radiology,
No.
simply by forcing it to look before it speaks and verify its claims against a visual reality, what other complex high-stakes human fields could this revolutionize? Think about law, where we've already seen AI hallucinate case files and invent precedents out of thin air.
Oh, definitely.
Or civil engineering, analyzing structural blueprints, or even financial forecasting. What happens when we take this architecture and force AI in all those fields to visually or factually ground its answers against an independent expert model before it ever generates a single word? Could we finally cure the confident bluffer for good?